Welcome once again to the physics video lecture. This is Physics 107B video lecture 8. We're going to start a new chapter today on waves, and we'll return to the material that we've been doing in when we start discussing some of the homework problems. So then we'll return to that, but we're moving ahead into chapter 9. And what we'll do is we'll start with the Maxwell equations. It doesn't take long to show that they lead to a wave equation. Then we go back to a discussion of waves in one dimension, waves on a string, a lot of stuff like that. So let's begin with Maxwell's equations. Equations, plural, in vacuum. So what that means is the charge density is 0 and the current density is 0. So rho vanishes, J also vanishes. And let's see what that leaves us with. We now have, that's not so good. We now have both the divergence of the electric field and the magnetic field vanishing, right? This one we always have. This is usually equal to rho, okay? So far so good. Then we have the curl of the electric and the curl of the magnetic fields. And which one gets the minus sign? Faraday. T, and then here we have mu naught epsilon naught dE dt. Mu naught epsilon naught dE dt. So we'll number these 1 through 4. And ponder them for a moment. So like I said, these look the same. These are also very similar. This term here is the one Maxwell added, and we see it for the equations in vacuum. We otherwise would have just had curl B equals 0. So that's the displacement current. And what we do next is we're going to take the curl of 3, and then we'll do the same thing for equation 4. So curl of E, right, that's a vector. We're going to exchange the order of differentiation here, so minus d over dt curl of B. Here on the right side, minus d over dt, the curl of B is mu naught epsilon naught dE dt. So mu naught epsilon naught dE dt. On the left side, we're just going to replace this with an identity. Curl of the curl, that would be the gradient of the divergence minus del squared of the field. So that's just an identity. That's del squared of each individual component of the field. And now we see we have divergence of E vanishing. And minus and minus will cancel. These are constants. We pull them out. I'll put this in the form d squared E dt squared equal divide by mu naught epsilon naught. So 1 over mu naught epsilon naught times del squared E. Good. We can do exactly the same thing, and we will, by taking the curl of this last equation here. both sides. So let's go ahead and do that. We already have one of our results. So similarly, curl of B equals u naught epsilon naught d over dt, and then we've got the curl of E. Now this time, on the right side, we're going to have the curl of P minus dp dt. So we're going to u naught epsilon naught d dt minus dp dt. And over here we do the same thing, gradient of the divergence of B minus del squared B. And the same thing happens. That goes to 0. The minus sign and the minus sign, they cancel. And I'll write this one the same way. We've got the second time derivative, d squared b dt squared equals 1 over u naught epsilon naught del squared b. Okay, so both of these equations are of course recognizable as wave equations. So we have in vacuum the possibility of electromagnetic waves. Okay. And we're going to study wave equations pretty thoroughly before returning to the electromagnetic wave equations. Again, you see the displacement current was the key for this even to happen. And we saw this displacement current, the applications we already saw were bridging a gap between parallel plates, for instance, okay, which this was not ad hoc, right? It was needed for the continuity equation to make sense. But here we have it, it brings us to the wave equations. Good, and these are 3 plus 3 because, each component, 3 components, electric and magnetic. Okay, so these are wave equations. But right now that's just a word, so what we'll do is systematically develop all the properties of these things in one dimension, in a system where we can really visualize everything, and then we'll return to the electromagnetic case. So next, waves. So the way we're going to start talking about waves is just as a disturbance that propagates through space. So, there's a disturbance that propagates through space. Like a stadium wave, for instance. And so if we want to, say, have some function, we're going to have some function f of z. There's a function f of z. And right now it's stationary. If this thing representing a disturbance were to propagate with constant speed, we could do that by just what letter am I using here? Still using F. Okay. Well, no, let's go ahead and let U of x and t equal f. And now I have to go for, gotta make up my mind, right? See what happens if we use x. Okay. U of x and t equal f of x minus v times t. We're just going to describe v is a constant, t is the time, x is the position. So yeah, when t is equal to 0, we have this original distribution. If we just let t run, then x minus vt being 0 would refer to this point here. So that point there is f of x equals 0, f of 0. And if the argument is 0, then that point at some amount of time is going to be over here. Okay, so this whole thing will propagate to the right with the speed v, just because that that argument, f of 0 is now for x minus vt equals 0. So yeah, that's why you immediately see that this is describing this disturbance here propagating to the right with speed v. And if I had a plus sign here, it would be propagating to the left with the same argument. So minus, plus, that's propagation to the right or left with speed v. Good. So that's the basic description of the simplest description of a disturbance moving to the right or left. And I'll even give a concrete example. I see I have a concrete example here. So, for example, u of x and t could be, yeah, great, some constant e to the minus, and I'm going to use that argument there, but I want to keep this dimensionless, so I'll use some letter b. X minus vt. So we'll have the propagation, and let's go ahead and square the whole thing. Squared, okay. So now we have a Gaussian type of distribution moving to the right with speed v. Good. And I see I have another example, so I'll do it. Or u of x and t equals some a sine. And again, to keep the thing dimensionless, I'll just have the b x minus vt. Okay. And this would, you'd have some sine with, some sine disturbance like that. But because of the argument, it's moving to the right. Good. So now we're going to get the wave equation. Next. The wave equation, and we're just going to differentiate. So we have u of x and t is equal to u of f x minus plus vt. So let's take two time derivatives and we'll take two spatial derivatives. du dt is equal to f prime of the argument times minus or plus v e squared u dt squared is equal to f double prime of the argument minus or plus squared b squared. So holding on to that, if we do two derivatives in space, d squared u dx squared, I don't even have to do them one at a time. We see it's just going to be f double prime of the argument. And from this squares away to 1, we see that d squared u dt squared is equal to v squared f double prime, which is say v squared d squared u dx squared. V squared d squared u dx squared. So there we have it. Just making contact with what we had up here. So some disturbance propagating with a constant speed. And now we see what this 1 over mu naught epsilon naught represents. It represents the propagation speed of this field of disturbance. Good. And yeah, there's actually an important note here, which I'll put here before we move on. U of x and t, slightly more general. We could since this is just linear operation, these differentiations, we could have f of x minus vt plus say g of x plus vt would also be a general solution to this differential equation. And that would be one part moving to the left and one part moving to the right. Moving to the right, moving to the left. So this is a general solution. All right, now next, we're going to go to an actual example, and our text does quite a bit of this wave on a string, and I think it's actually pretty good. So our next example is a wave on a string. And a bunch of properties of waves will be dealt with rather nicely with the wave on the string. So good. Next, wave on a string with a linear mass density, mu. So we'll take that as a constant, and the string is under a tension capital T. So we've got a stretched string under tension T. And for our sketch, we'll just take some point X, and we'll take some point X plus delta X. Here's our X-axis. And there's the string. I better give it a little like that. So we want to have an angle at both places here. So at the end of this, at the end points, we've got a tension in that direction and attention in that direction. So we have angles theta. We're going to call this theta prime, and we're going to call this theta, like so. And the transverse force is what we're going to do. So we're going to do Newton's law for the transverse force. Okay, so the transverse force is perpendicular to the x-axis here. So on the one hand, we have the difference in the forces in the endpoints, the transverse. So we would have t sine theta prime minus t sine of theta. Okay. Now, if we keep the amplitudes and the angles small, we would have t tan theta prime minus t tan theta. So small angle approximations. And of course, this can be thought of as the derivative, the slope. So we'll factor out t, and then we'll have df dx evaluated at x plus delta x minus df dx evaluated at x. So there's our force. Transverse force, perpendicular to the direction of x. And we'll continue with that. Okay, we can get rid of that too. Okay, so this thing approximates a second partial derivative. Okay, so I'm going to continue that right now. So we've got t d squared f dx squared. So I'm just going to write for the moment the approximation at x as delta x gets small, and if I had this divided by my delta x, that would be that partial derivative. So this square bracket is the partial derivative times a delta x, okay. Approximately speaking. So far so good. Now what about Newton's law on the right side? So we have this delta f is equal to m times acceleration, or delta f equals m d squared f dt squared. Again, that's that transversal acceleration perpendicular to the x-axis. And here for the mass, we've got the linear mass density view, so that would be u delta x, and then we have the d squared f dt squared, and now we can put them both together. So we have this and that, star and double star, okay? And in fact, when we equate them, because that's what we're doing here, when we equate them, we'll see we cancel the delta x on both sides, and we're left with, we'll just say limit delta x goes to 0, we're left with t d squared f dx squared is equal to mu d squared f dt squared. So we're going to put this, we're already seeing, we've got the wave equation again, we're going to put this into the form that we've had before. So we have d squared f dt squared is equal to t over mu d squared f dx squared. So once again, one-dimensional wave speed, and we can see that this tension divided by mass, linear mass density, gives us the speed squared again. So here, v squared is equal to t over mu. So for a, if you pluck a string, for example, strings under tension, you give it a pluck, then that plucked string is the disturbance going to propagate according to this speed, this equation, and with that speed. So let's look at the dimensions briefly, because this expression comes up in a number of scenarios. So you've got v squared tension, so that's force, and this is mass per length. Okay. So if you cross multiply, you'd have mass times v squared, and denominator to denominator, you have force times the length, so that's your energy. Okay, force times length is work, so energy. Cross multiply. Also, you'll have the case that we're not doing right now, but I should put it in here. In bulk matter, you will have v squared, and the dimensions I'll just put, so you'll have a force per area divided by a mass per volume. Okay, this is linear. You'll see dimensionally it's going to be the same thing. So force per area divided by a mass per volume, same dimensions as before. And the example would be v squared is equal to, say, E. Well, now we're getting into a different science, but I'll put this here anyway. This is an example from solids where E is the bulk modulus. Okay, not the electric field, the bulk modulus, that would be the density. So that's in bulk matter. Wave propagating through a solid can have this. Go ahead and erase this down. Or wave in a solid. And actually, all right, or liquid. It can be a little more complicated than that, but fundamentally that's what you have here. This is a bulk modulus. Okay, good enough. So anyway, we're back to this, the wave in the string, and we can analyze a bunch of things now in terms of what a wave in the string does. And the nice thing is you can actually pluck strings and rubber bands and observe these things, and it's a very, it's a system that's directly at hand. Okay, so having done that, we're going to look at the standing wave. This next development is really interesting. So make sure that was a wave on a string. Just did Newton's law. We've got the wave equation, recognize it again, recognize that as the speed squared, and so forth. So this time I'm just going to write down the expression for a standing wave, and then we'll apply the wave equation to it and see what happens there. So our next example is the standing wave. Important in music, for instance, in acoustics. So let's see what we have here. We'll take f of x and t, f of x and t is equal to a sine kx, and then we'll use the cosine of kvt. Cosine, put parentheses around kvt. So we don't actually even know what k is yet. We do think we know what v is, but we're actually not seeing the form of something propagating that we had before. Okay. So let's just see what happens here. We do know we have to multiply these things in here to make the argument of the sine and the cosine dimensionless. Okay. So that's what those things mean at the moment. You know, at some time t equals 0, then we would have cosine of 0 is a 1, and a sine of kx would just be sine, okay? So let's go ahead and look at the wave equation. So let's take some derivatives. df dt is going to be a sine of kx, and then we'll get a -1 sine of kvt, and the inner derivative will be k times v. Do a second time here, d squared f dt squared, a sine of kx. We've already got the -1 here, and then we'll get the cosine kvt, and kv comes out again, so that's squared. So that equals, got a minus, and then our original function f, so equals minus kv squared f. Now what about df dx? So df dx, we've got the cosine, bring the k out, do it a second time, we get minus sine back, and we get another k, so it's minus k squared f. And if we put these two together, we have d squared f dt squared is equal to v squared, that's what's missing here, d squared f dx squared. So d squared f dt squared is equal to v squared d squared f dx squared. So satisfies the wave equation. So this is a solution to the wave equation. And since it's not going anywhere, we can now see what's happening. First of all, this was for time t equals 0, and so you're just taking this pattern and multiplying it by cosine kvt. So it's just switching up and down in time t. So in that sense, it's not going anywhere, but at some point it's been reversed and so forth. Okay. So there's the meaning of that. Now we can do something else with this. the order that I'm going to do that in. Yeah, let's just hold on to this thing here. Okay. So next, consider the sine of kv minus xt. Okay. That's with the dimensionless and sine kv plus xt. Right, we know that these are a sinusoidal wave moving to the right and moving to the left, but we can use the addition theorems of the trig functions. So that's sine kv, got this backwards. Sorry about that. X plus and minus vt and not the other way around. Okay. X minus vt, x plus vt. There we go. We're going to use the addition theorems and just multiply these out. So we have sine kx cosine minus kvt plus sine kvt cosine sine minus kvt cosine kx. And here it's going to be the same with the change minus sign. So here we'll have sine kx cos kvt plus sine kvt cos kx. And if we add these two, right, the cosine is symmetric, no problem, it's going to stay the same, but these two are going to cancel because we've got a sine minus kvt, a sine plus kvt, cosine kx. So we just add these two, and we have sine k x minus vt plus sine k x plus vt. So those are the right and left traveling waves, is just equal to 2 sine kx cosine kvt. And you know, I could divide both sides by 2 if I wanted to, but you can see what we have here. This standing wave, which is on the right side, this standing wave, is the sum of those two traveling waves moving left and right. So standing wave equals the sum of two traveling waves moving in opposite directions. Which is pretty interesting. consult the clock. Okay, good. So this is an example of what's generally called a sinusoidal wave. And we certainly made use of that property because we used the addition theorem of the sine. Okay. So this next expression, sinusoidal wave. Apparently they play a special role. Okay, good. Sinusoidal wave. So now that we have the sinusoidal wave, we'll go ahead and write that down. And in terms of what we just had here, and what we'll then be able to tease out is kind of systematically what the meaning of this K is. So what you guys probably already recognize as the wave number, but we'll tease that out systematically here. Good, so now we have our sinusoidal wave. And I'll give the general expression for that. We're going to just write f of x of t, some constant. Use the cosine. Yeah. K x minus vt plus delta. X minus vt plus delta. So now again we have a traveling wave because it's a function of x minus vt, but it's argument of the cosine here. So this is going to be called phase, right? We know that this always repeats itself when the argument increases by 2 pi, and this is going to be the phase number. Okay, so that's the phase. I'll write these out here. So k x minus vt plus delta. Phase delta here is the phase constant. And you can see that this tells us how much something is delayed or not. So if we graph this, since it's just a cosine, if kx minus vt is 0, then this would just be cosine of delta. So we could just take the cosine and shift it a bit. Yeah. So we'll just shift this here, but otherwise it's just the cosine. Shift this by delta over k, but the wavelength we're just going to call peak to peak. And then we'll be able to relate k times the wavelength being equal to 2 pi apparently. So with k times lambda equals 2 pi. So now we have this k, it's called the wave number, 2 pi divided by lambda. So that's one thing. I'll put these in boxes here. Now the time required, remember this is a propagating object here, we could say would be v times t. So v times capital T is going to be lambda, a length. V times the time is equal to lambda. So T is equal to lambda divided by V. And now the lambda is 2 pi over K. From here, just cross multiplying times V. So there's the time required to propagate over a distance lambda. And furthermore, should get these a little more systematic this time. Okay, so there's the period. We can invert that. Frequency is 1 over period. And then if we do that, we can define omega times t, the angular frequency, as opposed to the counting frequency. The angular frequency as being equal to 2 pi. And this is the frequency that we use most commonly in our waves. So we can rewrite, we've got these points, we can now rewrite our wave as f of x and t is equal to a cosine. We've already got the kx, but now we're going to have kBt being equal to omega cosine kx minus omega t plus delta. Okay. That's going to be the standard form that we write it in. For a wave moving to the right. One more aspect of this that we want to get. So now we know what the K is. What if we take the minus K? So next, consider tilde here, f tilde of x and t equals a cosine minus k x minus omega t plus delta. So then we have the minus here. I can just continue. I can pull out the minus sign out of the whole thing. Okay, so a cosine minus kx plus omega t, and it doesn't have a minus sign, so minus delta. But the cosine is symmetric, so that's equal to a cosine kx plus omega t minus delta. So this is now the wave moving to the left. This was the wave moving to the right. And I got that just by changing the sign of k which tells us that this k, which is a wave number, actually has the vector property. Okay? When we convert from a wave number to a wave vector, we'll make use of that fact that we already had it here in one dimension. Okay. So I'll just finish here. K 2 pi over lambda. Wave number has the vector property. If you reverse the sign, you reverse the direction. Then reverse direction. Okay, so that's already a pretty systematic discussion of this. One-dimensional waves, starting with the waves on a string, and then talking about the standing waves, which you probably actually have even observed on the string in the lab, and then generating the sinusoidal wave definition, and now the wave number, angular frequency, vector property of the wave number. So that, I think, is a good place to stop for today, and we'll just continue with this next time.